everybody, and welcome to our module on the database environment. Let's see what has happened with databases in the past and where databases are today. In this module, we will dive right into the properties of a database, along with much of the vocabulary that people use when describing and analyzing databases. We will also look at many of the database models out there and put them into their historical and technical context. Then we will circle back to the relational database model, which is still the most popular model to hold structured data. So what makes a database, well, a database? First of all, we need to understand that even just the word database means different things to different people. Technically, when we have before us a collection of interrelated data items that are managed as a single unit, that already qualifies as a database. So think about all the apps on your phone, like your PayPal or your WhatsApp or Instagram. All of these data items relate to you, and you carry your phone around, you charge it, you run your system updates regularly, all that. So by that theoretical definition, your phone already is a database server and holds the database of you. But believe it or not, there are 5 common criteria for all these. The first one is management by a database management system, or DBMS. You have to have a software and hardware framework, otherwise nothing's going to happen. Secondly, a system must provide for layers of data abstraction. What that is, we'll see in a moment. Then there is physical and logical data independence, and lastly, the system must be able to organize the data in a model to store them, typically as objects. These are the 5 criteria that turn a system into a database management system. But what does all that really mean? Let's take a look at the first point, the database management system. That's why we're here, right? There are bazillions of database management systems out there, not just the big 3 traditional ones, MySQL, Oracle, and SQL Server, but also some newer systems such as Redis, MongoDB, Google's Firebase or BigQuery, and some graphical databases like Neo4j. All of these have different strengths, and typically you want to use them for different purposes. So what does a DBMS have to do to be worth its money? Well, it has to provide a structure to organize data, but also to allow us to move data around. The data has to be accessible to multiple users at a time, and they have to be able to update data without clobbering each other. It also means that whenever someone makes changes to data, which is called transactions, those changes have to be applied completely and uniformly, that is, across all the data, and we have to be able to undo, that is, roll back those changes. Now, you'll hear me say this multiple times. The purpose of a database management system is not to store data. You can use a file server for that. The main purpose of a database management system is to store data in order to allow you to retrieve data, aggregate them, and otherwise work with them to produce some sort of intelligence. That's why we need to be able to save, export, and import current and past state copies of our system, and why it's important to have security mechanisms in place to prevent unauthorized entities from accessing or modifying, even deleting data or even parts of our entire system. All of that is important because, again, the goal is to store and retrieve our information, preferably conveniently and efficiently. The second criterion that makes a database is that it allows for layers of abstraction. Think about it this way. Do you really want your mom or your employer to see everything that's on your cell phone? Yeah, I didn't think so. That's why we need layers of abstraction. Layers of abstraction help us surface only the data we want to specific users based on their need to see or manipulate them. For example, someone working in payroll processing may need to access your employee record to see the hours you've worked, whether you took any vacation or so, but does not need to access your performance evaluations. Whereas your boss needs this access to enter and modify your performance report, but doesn't need to see your paycheck information. That's why we have views. Views are something like stored filters or profiles that allow specific users to see and modify only specific data in the database. We call this the external layer, but more about layers up next. There are basically three layers of data abstraction. The external layer with the user-specific profiles or views about which we've already talked. Often these views also show up as dashboards with graphs and aggregated metrics. Then there's the logical layer. That's the area where the people work who organize, manage, and maintain the data and the health of the system. We're talking about database programmers, database analysts, architects, and some database administrators, or DBAs. This is the layer you see when you log into a database from the command line. The layer at the very bottom of our stack is the physical layer. This is where the actual files of our system live. This is the domain of your Windows and Linux system administrators, but also the DBAs who work with them on hardware and storage planning so that when table spaces grow too large and cover too many files on one machine, they can be relocated to another machine, that kind of thing. All three layers work together, and it takes a team of users, programmers, and administrators to manage and maintain a solid enterprise database management system. So what happens when data files grow bigger than what a server disk can physically accommodate? We obviously need to plan for that, right? Can we just connect another drive to the machine and change a few configuration options to ensure that new data is written to the new drive, but that we can still pull it into our reports and dashboards together with the old data from the old drive when needed? You bet we can. This is called physical data independence. Physical data independence means that we can move data files around, and if we set up our database management system's configuration correctly, the system will not just be able to store new data on new machines or concatenate different data from different files, but also keep track of the data so that we can easily retrieve it. If physical data independence means that a database management system keeps track of each data item, no matter in what file, on what machine, or on which drive the data is stored, logical data independence keeps track of the data even if the logical architecture of the system changes. This means that underneath all the table architectures that we as architects and engineers build, there is a meta layer of configuration tables that never loses a single data item, unless, that is, you choose to delete it. And if you choose to remove a data item or a column in a table, logical data independence means that any object that uses this data item or table column will also fail, but only if logged-in users log out and back in again. So, logical data independence is indeed the ability to make changes to the logical layer without disrupting existing users and processes, such as adding a new database object or adding a column to an existing database table. But how did we get to the databases that power the backends of Amazon.com, Facebook, or any university's electronic learning management system? Well, here's how. When air travel became more popular and affordable in the 1960s, American Airlines needed a way to keep track of its reservations and passenger lists at any airport in the world. That's when IBM developed Sabre, which was the first ever database management system that would deliver this kind of information over a network. Sabre revolutionized the travel industry. Only 10 years later, other software houses wanted to do the same thing, namely central data storage and distributed retrieval through client systems. That's when Mr. E.F. Codd's paper on how to architect a relational database system for maximum efficiency with minimal storage requirements did two things. Number one, it set an architectural goal for an entire industry, and number two, it provided a common graphical language in the form of the famous entity relationship diagram. These developments inspired the first big wave of commercial database systems, including Microsoft's SQL Server, IBM's DB2, and Oracle. In the 1980s, it became clear that there needed to be a standardized way of retrieving the data so that different database systems could talk to each other and 10 years later exchange information through APIs like JDBC and ODBC. That's how SQL, the structured query language that we use today, was born. And right away, databases became accessible not just to highly specialized and trained engineers, but to any programmer with good understanding of technical complexities and the ability to learn a new language. Remember, too, that in the 1980s, personal computers became commercially available, which means that we started producing more and more data. Mix that with the advent of the public internet in the 1990s, online shopping and the online payment industry begins. This is when OLTP, online transaction processing, and OLAP, or online analytical processing, become important for order fulfillment, tracking, and forecasting. At this point, every store owner needs a database, and anyone who can point and click in a GUI-driven database architecture tool like Power Builder wants to build it. In fact, even today, we're still cleaning up architectures from those days. This brings us to the last big technical milestone, the consolidation of the market and the firm establishment of the database giants Microsoft, IBM, and Oracle. In the 2000s, these companies reached their size by buying up smaller firms with great products like PeopleSoft or Fox Pro. But we're not stopping there. One thing giants are is slow, and these big three ended up falling behind market trends. Hardware, both in terms of storage and memory, has become cheap, so it's now less urgent to store data in complicated relational structures. Along with that, these days, data means more than names, numbers, and addresses. It means images, video files, emoji, and unstructured text that mixes all of these. It also means relationships between very rich data records, such as social media profiles, and the need to find the information you're looking for, that needle in the haystack, very quickly among a bazillion other data points. This is where engineers started experimenting with other architectures. What if we're breaking up relational structures and store anything in just flat files that can then be searched by an incredibly powerful search engine? That's how NoSQL started. What if the value of data is really in how they are connected? That's how graph databases started. What if a computer company doesn't want to maintain their own server room? That's how cloud-based services started, and so on. At this point, where hardware architectures allow us to quickly add any kind of storage and any kind of memory to our machines, the problems that past database architectures addressed have been solved. Today, the concern is about processing power, which is why embedded systems and parallel architectures are trying to address these. It will be interesting to see where nanocomputing falls in all of this in the future. The last criterion for a database is that it needs to use an architecture to store data. This is also called a database model. Don't confuse that with a data model. A data model describes how specific data is stored in specific tables and what the relationships are among the data. A database model describes the architecture that defines what kinds of relationships tables are designed to have. So put yourselves in the shoes of the early database designers with their bell-bottom jeans and the Beatles records. You have a number of airplanes anywhere in the world. You have passengers on those airplanes that want to fly to a number of destinations. How in the world do you organize all that? The first option is to store data in flat files. Remember, it's the 1960s, and you're wearing bell-bottom jeans, and President Kennedy is in office, and there is no Google or even Yahoo or any other search engine. All you get is this. And you're going to have to tell me how many people are going from Chicago to Frankfurt, Germany on my Boeing 707 tomorrow morning at 9:02 a.m. You would have to figure out how to read the passenger file, find the file that contains my available airplanes, their locations and flight plans, and that's just the beginning. Then you would have to write a lot of parser code to read and correlate each file's contents, and then your code would be specific only to those files. Yeah, no, not a good idea. But what if we think in terms of hierarchical connections? What if we added pointers to that file where those pointers connect the airport file to the available planes files and the planes file to our passenger file. But then what if a passenger decides they want to fly to Costa Rica instead of Germany? We would have to build an entirely new model just for that one case. The hierarchical model has put us into data jail. That leaves us with our third option, the network model. This is very similar to the hierarchical model, only that our pointers are named and bidirectional. So the programmer can direct the database to use a particular relationship to get from one record to another. That's kind of how our modern graph databases work, but remember, we're in 1960 and there's no Facebook or Instagram, so it's really hard to imagine networks of data. But what we do know back then is that we can code with objects. Now, the C programming language is just about to come on the scene and turn object-oriented programming into a thing for the programming masses, but we already have something called CPL, or Combined Programming Language, that allows us to think in terms of classes and objects and variables and methods that we can attach to classes or even specific objects. So if we choose to make an entity an object, like customer or airport or airplane, then we can store its characteristics in the object's variables. We could connect objects with methods, and we could possibly write enough methods to find out which passengers flew to Dallas in 1963. But that would require writing new methods each time we want to connect our objects in different ways, and that's too much work. So we need a database model that allows us to store any kind of record, organize it into entities, and not change that structure every single time we need to pull any information out. That's where the relational model comes in. In a relational model, we keep our records in simple two-dimensional tables with horizontal attributes and vertical row numbers, and we store pointers along with some of those attributes directly in the table. But all those pointers, called keys, really do, is identify which other table contains the same related data item. That's genius, because it allows us to connect attributes from one table to the next, set up that external layer, those views, based on the attributes we have identified in a table, and we can query entire table columns rather than just one object. Genius! So here's how the relational model works. Let's look at the diagram first. We see that we have 5 objects or entities that are connected: employees, customers, orders, order details, and product. Let's focus on the relationship between customers, employees, and orders and think about our airplane passengers buying their suitcases. We want to know which corporate customer has ordered 100 black suitcases and which one has ordered 50 red duffel bags, right? And we want to be sure that the employees who sold those big orders can be sure they are packed correctly and sent to the correct address. So we need to capture our customer information here. The easiest way to track the entire order would be to write the customer name and address into each order. But that would mean entering the same information multiple times, because the customer who ordered the black suitcases may have also ordered a black backpack. So we give our customer a customer ID when we store their information. Now, for each order, instead of repeating the customer's name and address, all we have to do is store the customer's ID along with the order. And just like a hyperlink on a web page, that customer ID takes us right back to the original customer record. That is extremely practical with customer number 6 that you're seeing here, because we're sending them the black suitcases and the black backpack and don't have to deal with any typos in the address because we need to enter it only once in the customer table. We do the same thing with tracking the employees who are tracking the orders. All our employees have ID numbers, in the same way in which you may have a student ID number. So now we can store their employee ID number in the order table along with each order. And we will always know by looking at the ID number up in the employee table later, who is responsible for the order. In fact, we can see that employee number 2, who happens to be our vice president of sales, is responsible for 2 orders, and both of these orders went to customer number 6. So we see that you can connect one customer to many orders and one employee to many orders as well. And by virtue of this relationship, you know too which employee is working with which customer. So stop this video for a moment and check if you can identify these one-to-many relationships in the drawing above as well. As you can see, connecting tables, that is, establishing relationships between data through the power of keys, is the power of relational databases. We have now seen how relational databases have a number of advantages. If you have insight into one table, all you need to do is follow the bunny trail from one table to the next along the matched keys. These linkages make a relational database model like chainmail, in which, ideally, every data point can be connected to every other data point. It also makes relational databases still the preferred way for businesses to store data in, although that is changing slowly as well. However, if you set foot into a company or any other organization now, chances are that you will most likely encounter MySQL or any of the enterprise powerhouses of Microsoft SQL Server, Oracle, or IBM as the backend of the majority of applications that the business runs every day. So let's look at what we have learned. We have discussed the properties of a database along with much of the vocabulary that people use when describing and analyzing databases. We have also looked at many of the database models out there and put them into their historical and technical context. Lastly, we have taken a close look at the relational database model and seen how data in tables is connected with the help of keys. This allows us to be economical on storage space because we don't have to repeat or duplicate information, which was a huge concern in the days in which hardware was really expensive. Hardware is much cheaper now, but IT departments are constantly asked to do more with less money. That's one reason why relational databases are still the most popular model to hold structured data.